Have you ever wondered how machines can understand and remember sequences of data? How they can remember the past to predict the future? Well, the secret lies in an advanced type of neural network known as long short-term memory, or LSTM. Neural networks, at their core, are computational models inspired by the human brain's structure and function. They consist of layers of nodes or neurons, each performing simple calculations. Data flows from the input layer through one or more hidden layers to an output layer. These networks are excellent at recognizing patterns in data, making them handy for tasks like classification, regression, and even image and speech recognition. But there's a catch. Standard neural networks process inputs independently, without considering the sequence or order of data. This limitation led to the development of a new class of neural networks called recurrent neural networks. Recurrent neural networks, or RNNs, are distinguished by their memory of previous computations. They take into account not only the current input, but also what they have learned from previous inputs. This makes RNNs suitable for time series data, natural language processing, and any task where the sequence of data points is crucial. However, RNNs have a significant drawback. They struggle with long-term dependencies. As the gap between relevant information grows, RNNs become unable to learn to connect such information. This problem, known as the vanishing gradient problem, is where LSTM networks come into the picture. LSTMs are designed to solve the problem of long-term dependencies. They achieve this through a complex architecture that allows information to be retained or discarded over long periods. An LSTM unit includes several gates: the forget gate, which decides what information is discarded from the cell state; the input gate, which updates the cell state with new information; and the output gate, which determines what the next hidden state should be. This structure enables LSTMs to remember information for long periods and decide what to store, modify, or erase. So what sets LSTMs apart from traditional RNNs and standard neural networks? 3 key points. Firstly, the memory capability. While RNNs remember previous inputs for a short duration, LSTMs can maintain this information over much longer sequences. Secondly, the architecture complexity. LSTMs have a more complex architecture than standard RNNs due to the presence of multiple gates controlling the flow of information. This complexity allows them to perform better on tasks requiring an understanding of long-term dependencies. Finally, their versatility. While standard neural networks are highly effective for a broad range of tasks, their lack of memory makes them unsuitable for sequential data where context and order matter. RNNs address this issue to some extent, but LSTMs take it further by efficiently handling long sequences. In conclusion, LSTMs, with their unique architecture and memory capability, have revolutionized the way machines understand and remember sequences of data. So the next time you marvel at a machine's ability to predict the future based on the past, remember, there's a good chance an LSTM is working its magic behind the scenes.